Okay, we're going to continue to talk about oxidation and reduction, and now we're going to start to put it in context of electrochemistry. So right now we've just kind of accounted for electrons moving, and now we're actually going to apply that and do something with it. So today's first part is about voltaic cells. And so voltaic cells are also known as electrochemical or galvanic cells. And these are what batteries are, ultimately. And it's a spontaneous reaction, meaning that it happens without outside intervention. What we're doing is we are converting chemical potential energy into electrical energy. We're generating a current here. And so we're going to separate these two half reactions that we've been talking about and run the electrons through an external circuit. And in doing so, we're making electrical energy. We're not going to lose this energy as heat. So a half cell is where the half reaction occurs. And it's usually a piece of solid metal submerged in an aqueous solution of its own ions. Now, every now and then you'll see something that has an inert electrode or, say, like graphite. So something that's a conductor, and this will be your electrode submerged in an aqueous solution. Okay, but right here, there's no net reaction going on. Okay, there is an equilibrium between the solid copper and the copper ions that are here in this copper 2 ions that are in the copper sulfate. So there's an equilibrium, there's a back and forth, but there's no net change. Okay, so here's the general idea of what a voltaic cell looks like. So take a minute and you're going to draw this, and then we're going to label it. And we'll talk through it. There's a lot of text, but just take a minute, draw it, label it, and we'll go from there. Okay, so each of these is a half cell. So these two submerged pieces are your electrodes, and we can connect them through a wire and a voltmeter, which would tell us how much electricity is being produced. Okay, so these are our two electrodes, and each of these is a half cell. And then they're going to also be connected not only by this external circuit, but also by a salt bridge. Okay, this salt bridge is going to allow some electrical conduct between the two solutions. It's going to prevent mixing of those solutions, and it will maintain the electrical neutrality because, like a bridge, things travel across it. And so we're actually going to have some flow of ions. So a salt bridge is usually something like it's either a glass tube that's shaped like a U and it's filled with agar, like what's in a petri dish that's saturated with potassium nitrate or sodium nitrate, or it could be a saturated piece of like filter paper that's saturated with the sodium nitrate or potassium nitrate. Okay, so your electrodes are going to flow from those through the electrodes from anode to cathode through this external circuit. And so we're going to add to our picture a little bit. Let's call the cathode the one on the left and the anode the one on the right. It doesn't have to be, but it will be here. The cathode is the site of reduction, and the anode is the site of oxidation. So what that means is that at your cathode, you've got the aqueous ions are going to gain electrons and become solid. So you'll actually see an increase in mass of your cathode. Your anode, the solid ion or solid atoms that make up your anode will go into solution and lose their electrons. So the electrons are going to go through this external circuit from the anode to the cathode. So the electrons go in alphabetical order, anode to cathode. Now, that salt bridge has ion movement. Your anions are going to move opposite direction of electrons. So here they'll go cathode, or they'll always go cathode to anode. But your cations, which are positive, will go the same direction as the electrons. Okay. Now, to help you remember what's what, Anox, red cat. Anode, oxidation. Reduction, cathode. This is true no matter what. Okay, so let's try a real example. Okay, the zinc and copper cell. So take a minute. This is partially drawn, but I want you to label what's there. And then we'll talk through this. Okay, so if you were to look at your activity series, you would see that zinc is higher up on your activity series, meaning it is more likely to lose electrons. It is more likely to be oxidized. And so if we think about the fact that there's an equilibrium happening between the zinc atoms and the zinc ions, we could say that the zinc has a higher tendency to lose electrons than copper. Okay, it's more reactive. And so the equilibrium will lie more towards the zinc ions than solid zinc. The opposite is true for copper. So we could say that there's more electrons in this electrode. You don't have to draw this part. So it has a larger the copper electrode is going to be less negative than the zinc. So then if we connect them, electrons will flow. Okay, now right now, there might be electrons flowing a little bit, but not much. There's certainly nothing going to read on the voltmeter. Why? Because we don't have our salt bridge. Okay, so draw in your salt bridge as well. By the way, these are pieces of like cotton. I know, beautiful artwork, right? So here is your zinc copper cell. Zinc is more reactive, so it is oxidized. The electrons leave the zinc electrode and travel through the external circuit to copper, to the cathode. As these electrons come in, the copper cations are attracted to those negative electrons and come and gain the electrons and become solid copper. Okay. Now, taking care of all this charge, your anions, because electrons are going, the way you're looking at your screen, they're going left to right. So your anions, which carry electrons, are going to move right to left, and your cations left to right to kind of neutralize all that charge, or not neutralize it, but to maintain electrical neutrality. Okay, so again, your zinc is your anode. It's where oxidation is occurring. Your cathode is where reduction is occurring. Now, you might have noticed that all the copper solutions that we've dealt with have been a real nice, pretty blue. Well, one of the things that you would notice in this scenario is that as more and more copper plates onto your electrode, that the intensity of this blue solution is actually going to decrease because there's less copper ions floating around in here. Zinc is colorless, so you won't notice any change there. So let's try this. We're not going to draw out all of these, but we're going to talk through them and see if we can figure out who's the cathode, electrode, and what's happening. So it says use the metal reactivity series above, or in your data booklet, to predict which electrode will be the anode and which will be the cathode when the following half cells are connected. Write half equations for the reactions occurring at each electrode. Then write a balanced equation for the voltaic cell. So our first one deals with zinc and iron. So we're going to look at the activity series, and we're going to see that zinc is higher than iron. So that means zinc is more likely to be oxidized. So we're going to write a reaction for zinc being oxidized, for losing electrons. And oxidation occurs at the anode, so zinc is the anode. That means that iron is going to be the cathode, and it is going to be reduced. So I'm going to write iron gaining electrons. Go ahead and say that iron's a cathode. Now, something to note, state symbols, they matter here. Okay, so make sure you have your state symbols. Your ions are going to be aqueous. the neutral atoms are going to be solid for metals, unless you're dealing with mercury, but we don't play with mercury, right? Okay, balanced equation for the overall cell. Well, we've got our two half reactions. They're both balanced, and we have 2 electrons being lost, 2 electrons being gained, so I can just add those two and cancel everything out and get that. Okay, I want you to try the next 2 on your own and then check your work. So for this one, you'll notice that we have iron and magnesium. Magnesium is higher on the activity series, so it's going to be oxidized. So there's my equation for magnesium being oxidized. If it's oxidized, it's the anode. So that means iron is going to be reduced, and it's the cathode. I have 2 electrons gained, 2 electrons lost, so I can just add those together. Make sure you have your state symbols, and there you go. And lastly, we have magnesium and copper. Again, magnesium's the more reactive. It'll be oxidized, so it's the anode. Copper's our cathode, gaining electrons. Okay, notice that on none of these, if you're dealing with a voltaic cell type question, you're not going to have to balance electrons and get all that squirrely stuff going. We take one task at a time. Okay, let's look at this next one. It says, draw a voltaic cell with 1/2 cell consisting of magnesium and a solution of magnesium ions, and the other consisting of zinc and a solution of zinc ions. Label the electrodes with the name and charge, the direction of electron and ion movement, and write equations for the reactions occurring at each electrode. So, we're going to do that. Alright, so I've got zinc and magnesium. Here's my 2 beakers, my 2 electrodes. Okay, I'm going to say that this is a zinc solution. So this is solid zinc. Here's my magnesium, solid, and my magnesium. Now I'm going to look at the activity series to figure out what happens. I mean, if you want, you can go ahead. There's our external circuit. Here's our salt bridge. I know, beautiful artwork. Here's my little fluffy cotton balls. You don't ever have to draw the cotton balls. Don't worry about that. Okay, activity series. We look at the activity series. Who's more likely to be oxidized? It's magnesium. So I'm going to write an equation for magnesium being oxidized for losing electrons. So it's going to go into solution. So this is oxidation, which means that electrode is our anode. So by process of elimination, this is our cathode. Zinc is going to be reduced. So plus 2 electrons. Okay, so we said label the electrodes with the name and the charge. Okay, well, we haven't talked about the charge of the electrodes yet, but this is actually really important. Okay, our electrons are going to flow from anode to cathode. Okay, so our cathode let me back up. This electrode, the anode, having electrons in it as the atoms are leaving and going into solution, is going to be negative. Not that it actually has a negative charge, but relative to everything, it's negative. Meanwhile, we've got zinc ions hopping onto our cathode, giving it a relative positive charge. So in a voltaic cell, the anode is negative and the cathode, with a little t in it, is positive. Okay, so we labeled the electrodes with name and charge, the direction of electron and ion movement. So here's where we have our salt bridge. So we're going to have anions moving and cations moving. Remember that cations are going to move the same direction because they're positive. They're going to move the same direction as the electrons, and our anions are going to move the opposite. So they're providing our constant stream of electrons and completing the circuit. And we wrote our two equations. So there we go. Okay, here's our next one. Oxidation reduction reaction, and we have dichromate reacting with hydrogen and iodide to form chromium-3, iodine, and water, and it's spontaneous, so it tells us all about this. A solution containing potassium dichromate and sulfuric acid is poured into one beaker, and a solution of potassium iodide is poured into another. A salt bridge is used to join the beakers. A metallic conductor that will not react with either solution, such as platinum foil, is suspended in each solution, and the two conductors are connected with wires through a voltmeter or some other device to detect an electric current. The resultant voltaic cell generates an electric current. Indicate the reaction occurring at the anode, the reaction occurring at the cathode, the direction of electron migration, the direction of ion migration, and the signs of the cathode and anode, by the way. So the first thing we need to do here, because this isn't on the activity series, you need to assign oxidation numbers so we can figure out what's being oxidized and what's being reduced. Okay. So here you go. Okay, so if we notice, chromium is going from +6 to a +3. So chromium is reduced. So okay, and so oxidation is dealing with the iodine. Now that we have what's being reduced and what's being oxidized, we can draw and label our picture. So we're going to have our two beakers and our platinum electrodes connected by the external circuit and our salt bridge. Let's see if I can do a better job with our salt bridge this time. Okay, so let's say that this solution is the dichromate. And over here is our iodine. So we're going to indicate the reaction occurring at the anode, the one at the cathode, the direction of electron migration, and the direction of ion migration, and then the signs of them. Well, we already did a little bit of this because we know what our reduction reaction is. So red this is our cathode, and cathodes are positive. So this is our anode, which is negative. Okay. For our reaction, we'll go ahead and balance it. So balance the chromium. Now I've got to balance the waters. And because this is a half reaction, we are going to have our electrons in here. So I've got 2 times +3, so that's +6. And then I've got a +12 over here, so I'm going to add in 6 electrons. And over here, I have iodide forming iodine. So I'm going to have 2 of those and then plus 2 electrons. Okay, and electron migration. Electrons are going to move from anode to cathode, which happens to be right to left on this one. And then the direction of ion migration, where we have our anions and we have our cations. Our anions move opposite the electrons. Our cations move the same direction as our electrons. And there you go.